Let's take a look at this problem from winter 2021. It's problem 8. And the first part is asking us to find an explicit expression for the average rate of change of this function between q equals to 5 to q equals to 5 plus k, where k is some non-zero constant here. And they do ask us that our answer should not have the letter L and not attempt to simplify our expression at all. So let's actually think about this. So let's start with part A. Well, we want the average rate of change. Average rate of change is just the change in output divided by change in input between two different input points. So here the input is changing from 5 to 5 plus k. So q here is the input, which is changing from 5 to 5 plus k. So the change in input from 5 to 5 plus k is k. So you're dividing by k. So let me divide entire thing by k. What about the change in output? Well, change in output of a function from 5 to 5 plus k is simply going to be L of 5 plus k minus L of 5. So remember, this L of q is the output, and our input is changing from 5 to 5 plus k. So L of 5 plus k minus L of 5 is exactly the change in output. But we do not want our answers to have letter L. So you actually have to plug in this 5 plus k into q, and we have to plug in this number 5 into q to actually simplify these two expressions. So we know L of 5 plus k, when I plug 5 plus k into L of q, is sine of 5 plus k over 1 plus 3 times 5 plus k. And remember here, the 5 plus k is really one quantity. This is one thing. So you really have to put parentheses around 5 plus k. Like if we do not put parentheses, for example, if I write something like sine of 5 plus k, this might be interpreted as sine of 5, then adding k, which is not what you want. You really want to do 5 plus k, then take sine. And obviously, if I omit parentheses here, this might be read as 35 plus k. You don't want that either. So make sure you put the parentheses around the 5 plus k, and we're subtracting L of 5. So now q is 5. So I just plug 5 into it. It's like sine of 5 over 1 plus 3 times 5. We don't have to simplify our expression. So this is all there is for part A. This is just average rate of change, which is change in output divided by change in input. Part B is a little more involved. Now we want to use the limit definition of the derivative to write an explicit expression for p prime of 3, and p of b is this function. B is the input, this is the output. And remember, how does the limit definition of derivative work? Well, how it works is that we have some sort of curve. So maybe this is the graph of p of b. So here we might have the b-axis, here we might have the output axis, and we have p of b, the graph of p of b going something like this. And we have some point, say b equals to 3, where we're taking the derivative of. So here, maybe this is b equals to 3, and you want to find p prime as 3, which by definition, remember that p prime of 3 is just the slope. P prime of 3 is just the slope of this tangent line as 3. And the way we attempt to find the slope of this line is as follows. Well, we only know so far only one point on the line. If I only give you 1 point, then finding the equation of the line is impossible. You can't really do that. But if I give you 2 points on the line, you can find the equation of the line. That's not too hard. So what we're going to do is we're going to move a little away from 3. So we're going to say add h. So do plus h from 3, and now you're at 3 plus h. And this gives you another point on the curve. So if this point is at 3 comma p of 3, now you have a point at 3 plus h comma p of 3 plus h. And what we're gonna do is we're gonna try drawing a secant line. So a secant line is a line going through these 2 points. And what I'm going to do is I'm going to find the slope of the secant line, and I'm going to use that to approximate the slope of the tangent line. And here's the key thing. Obviously, this approximation might not be exact, but as we move h, as we move this h closer and closer to 0, so as h is shrinking towards 0, this 3 plus h is moving closer and closer to 3. So as this point, so another way of saying it is as this point is moving closer and closer to this red point, so as h is shrinking towards 0, we're moving this point closer and closer, the secant line is going to start approaching the tangent line. So as h is approaching 0, so as h is approaching 0, the slope of the secant line is approaching the slope of the tangent line. And this is really the key idea behind the limit definition of the derivative. So here's what we want to do. We first want to take limit as h goes to 0, because this is the entire point. We approximate using a secant line, and we take the limit as h goes to 0 to actually find the slope of the tangent line at 3. So we are going to take limit as h goes to 0. And what is the slope of the secant line here? Well, again, we're given 2 points. We're given the input of 3. The output is going to be p of 3. We have another point. The input is 3 plus h. The output is p of 3 plus h. We just have to do change in output over change in input. It's like change in y over change in x to find the slope of this line. So that's simply, we simply want to have p of 3 plus h minus p of 3 divided by change in x, change in input, which is h. But now here's one problem. They do not want our answer to have the letter p. So we actually have to, once again, plug in this 3 plus h into b here. And we want to plug in 3 into b here to rewrite it in terms of the actual expression for p of b. And again, this is we just have to do it. So limit as h goes to 0. You plug in 3 plus h. Again, this is one quantity. Make sure you put the parenthesis around 3 plus h when you plug it in. So we have natural log of the quantity 3 plus h. And this entire thing, see how they're putting parentheses around natural log. So this entire thing is being raised to tangent of 3 plus h. And I'm going to subtract it from when I plug in b equals to 3. So I'm going to subtract it, natural log of 3 raised to tangent of 3 here. And I'm dividing this entire thing. And I'm dividing this entire thing by h. So this is the answer we want.